Hey guys, all right, so I'm back here to do the second part of the section 3.6 notes video, which is going to cover the composition of functions and the uh, domain of compositions. So we are going to start looking at compositions of functions, which is a different type of combination. And in a composition of functions, we are going to be substituting either the result of one function into another, or we will be substituting the entire actual function into the other. So it will depend on what the notation looks like. But in one situation, you're given a value, and the other one you are not. The notation looks like either this or this. The first one, f of g of x, means that you are going to be putting the g function into the f function, or the output of the g into the f, depending on whether or not you have a value. The other one, g of f of x, means that you are going to be putting the f function into g. So regardless of what the notation looks like, when you're dealing with compositions, you work your way from right to left. And it's very important that you do it in the correct order, which is like backwards from how we normally do it. So we want to make sure that we do it correctly. The first scenario that we have is where we are going to be given functions and given an actual value to go into the functions. Now, since we're working from right to left, I'm going to begin by taking the value and putting it into the function immediately next to it, which in this case is the f function. So I want to start by finding f of -2. That means -2 is my input value for this f function here. 3 times -2 plus 1. And then we evaluate. So this is -6 plus 1, which is -5. Now, in the algebra of functions where you're doing the operations, you would evaluate the second function using the same value. In a composition of functions, we don't do that. Instead, these are going to build on each other, and whatever the output is from the first substitution becomes the new input for the next function. So this is the new input, and it's going into the g function. So that means for the second step, I'm finding g of -5. And so I plug into the g function this time. -5 squared minus 2 times -5 minus 6. And -5 squared gives me 25. -2 times -5 gives me 10. And then minus 6. Now, once I evaluate this, 25 plus 10 minus 6, that's 35 minus 6 is 29. This value is your final answer. There is no additional operation to do like when we had the algebra of functions. Whatever you get for your final output is your final answer. So you're inputting from right to left, and these things are building on each other. Now, when we don't have a value, the notation is going to look similar to the algebra functions, except it's a composition. So f of g of x. This does not mean that you put x into g. X is already in g if you look at the g function. It's right here. So we're not going to do an additional substitution of x in there. It's just notation saying we're working with the functions themselves. What this is really saying is that I'm taking the g of x function and putting it into the f function. And this is going to look a lot like the substitution method from when we did systems. You take an expression and you put it into another function, replacing the variable. So this is going to look like 2 times x plus 7 squared minus 3 times x plus 7. And now we have this algebraic expression that we have to go through and simplify. And we want to make sure that we use order of operations when we do that. So I'm going to begin with the squaring. It really means that I'm taking x plus 7 and multiplying it by itself. So I'm going to begin here. This is x squared plus 7x plus 7x plus 49. And then when I combine these like terms in the middle, I've got x squared plus 14x plus 49. And that's the squaring. And now all the rest of the pieces are going to come back in. 2's on the outside minus 3 times x plus 7. And the next step in the order of operations is multiplication. So we're going to distribute. 2 times x squared is 2x squared. 2 times 14x is 28x. 2 times 49 is 98. Negative 3 times x is negative 3x. And negative 3 times 7 is negative 21. All right, so once we have everything multiplied out, now we're going to go back through and combine the like terms. 28x's minus 3x's. That's 25x's. And 98 and negative 21 combined to give me 77. That leading 2x squared didn't have a like term, so it just stayed. And now this guy here is your final answer. So with an input value, we get an output value at the end. And typically with no input value, since you're putting an expression in, you're going to get an expression out. On a rare occasion, all the x's would cancel and you would get a number, but that would be kind of like a rarity. It's possible, but usually not likely. All right, let's see here. Let's get into some domain stuff. All right, so when we are trying to find the domain of a composition, it's a little bit different than the algebra of the compositions. I mean, the algebra of functions domain, because in the algebra of functions, you didn't necessarily have to know what it looked like when you did the formula. In compositions, you are going to need to find what the composition is because its domain will come into play when you are dealing with the domain of all of this stuff. So it's very important still that we find the domain of the individual functions. We want each one individually, and we're going to use the number line again so that we can take a look at where they overlap. But once we have the domain of the individuals, we want to actually find the composition. Whether it asks for the composition or not really doesn't matter. We still are going to need it. Then, once you have the composition, you want to find its domain as well. Now, all of this stuff that's down here is the same. We're looking to see if it has fractional excluded values. We're looking to see if it has a square root because we can't have anything negative. So all that stuff is the same. But all three of these things are going to come into play together. We want the domain of each individual and the domain of the composition. And we're going to put all of them on the number line together and see where all three of them overlap. All right, so here's my example. And this example is the more involved of the two, so I'm going to go through this one because it has these rational expressions, which means it's going to have a little bit of work to do. Now, before I even get started with the composition, I'm going to go ahead and just list out what the domain of f and g are, just so that I know. And that way, at least I have an idea of what I'm going to be working with. Let me see how much space I can give myself. Well, this much. Okay, so starting with domain of f. Okay, so the f of x function is right here. It is a rational function. When we have rational functions, we have to be concerned about excluded values, which are values that create a zero denominator. So to figure out what the excluded value or values are, we are going to take the denominator and set it equal to 0. Now, when we set this thing equal to 0, we create an equation. This is a very basic equation that doesn't actually need solved because it's already solved. But if it had to be solved, we would isolate our variable. Whatever we get when we isolate is going to be the domain of the f, removing this value. So the domain is everything except 0. That looks like negative infinity comma 0, u 0 comma infinity. In a similar fashion, I am going to find the domain of g. And it is another rational expression, which means that I'm going to take this denominator now and set it equal to 0. 2x plus 1 equals 0. This is a two-step linear equation. We are going to subtract 1 over. That gives me 2x equals negative 1. And then to get x by itself, divide by 2. So x is negative 1/2. And this is your second excluded value. So to write that in interval notation, 0 comma negative 1/2, u negative 1/2, comma infinity. So this is going to be kind of the jumping off point for our domain for each one of these compositions, because you can't have a 0 in the first one and you can't have a negative 1/2 in the second one. So this is going to cause a problem. So now let's find our compositions. We want to start now with the composition f of x, or f of g of x rather. And let's do f of g of x. Remember, these are worked right to left, so that means the g function is going into the f, taking this whole thing and putting it under here in the denominator. That looks like 6 over 1 over 2x plus 1. Now, this here is a complex fraction, and it cannot remain, so we're going to have to rewrite it by doing keep it, change it, flip it. Multiply by the reciprocal. 6 over 1 times, flip this guy over, 2x plus 1 over 1. And then we are going to actually multiply this out. 6 times 2x is 12x. 6 times 1 is 6. So this is my composition. And what's nice about this composition is that this thing is linear now. There is no more rational expression because there's no more variable in the denominator. So linear functions don't have any additional restrictions. The only things that are going to have more restrictions are more rationals or more radicals. So in this case, our domain is going to be built off of the original domain. And so I'm going to put this thing on a number line so we can kind of take a look at it. Here's my number line. And we've got -2, -1, 0, 1, 2, 3. The first domain is everything but 0. If we put that on the number line, it's going to kind of look like this, shading off to the left, shading off to the right, just not touching 0. And then the second one is everything but -1/2. So that's about right here. And again, everything shaded off to the left, everything shaded off to the right. Now, the overlapping part of this is where these two things are in common, and it's really hard to see here. But there's purple and red all right here. Maybe I should use a highlighter. There's purple and red all right here. Cut out the negative 1/2. There's purple and red right here coming up to 0. Cut that out. And then there's purple and red all the way across here. So in interval notation, it's going to look like negative infinity up to negative 1/2. Cut this guy out. Then negative 1/2 goes to 0, but we have to cut that guy out. And then after 0, we're good to go all the way to infinity. So this is the domain of f of g, which is technically the domain of f and g put together anyway. Now we're going to do g of f, and then we'll find the domain of that as well. Let's kind of separate this a little bit. So here's the first, there's the domain. Now we're going to find g of f, and then we'll find the domain of that. So g of f of x. This is where we're putting the f function into the g function. So we're taking this function here and shoving it underneath here. That's going to look like 1 over 2 times 6 over x plus 1. That can simplify a little bit to begin with. 2 times 6 over x is 12 over x plus 1. Now, we cannot leave it in this form. So there's a couple different things that we have to do. First of all, we need to combine these terms under here in this denominator. And to do that, we're going to need a common denominator. So the LCD is x because it's the only denominator. And we can rewrite a 1 using x if we put x over x. So this is going to look like 1 over 12 over x plus x over x, which becomes 1 over 12 plus x over x. Now, we're in a similar situation at this point that we were in this first example because we have a complex fraction. So in similar fashion, we're going to have to keep it, change it, flip it, and make this 1 times x over 12 plus x. And 1 times anything is itself, so really this is x over 12 plus x. So here's my composition. The issue is now that this is another rational function. So just like we did with the two original ones, we are going to have to figure out what the excluded value is for this guy as well and put it with the original two domains. So let me get a different color. We'll use this purpley color here. And for domain, we're going to have to, here, let me separate this too because it's kind of turning into a giant mess. For domain, we're going to have to take this denominator plus x and set it equal to 0. This gives us another excluded value, which is negative 12. So in addition to the two original ones, which were negative 1/2 and 0, we also cannot have a negative 12 either. So let's see what happens when we put all of this stuff on the number line. Oh gosh, okay. Okay, so let's say we've got negative 14, negative 13, negative 12. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, -2, -1, 0, 1, and 2. Okay, just save some time. That looks like it says 12. I'm going to move this 1 over a little bit. 1. Okay, so just imagine this is completely filled in. All right, so we have for our first domain back at the very beginning, we could not have 0. So we did that one in red. 0's right here. We've got open parentheses, but the shading goes off in both directions all the way. It's just 0 that's no good. In the second one, we had -1/2. So again, we had open parentheses on -1/2, but the shading went everywhere again besides -1/2. And then for this third one, we now have another excluded value at -12, which is here. But shading's going to go everywhere again from one side to the other. Now, because, again, it's really hard to use this highlighter, so we had these round parentheses on -12, and the shading, triple shading, continued all the way up to where it hit -1/2. And then it continued a little bit further to 0, and then it went off here. So that's where all of this stuff overlaps. Ignore this because we're not going to do this one. So for domain of G of F, we have -infinity to -12. Cut that one out. -12 up to -1/2. -1/2. Cut this one out. -1/2 up to 0. Cut that out, and then we get to go to infinity. So 3 excluded values. So similarly to what happened in the algebra stuff, we have to do some extra checking. In the algebra ones, we only had to do the extra checking for division because domain of the other 3 was just wherever the original 2 overlapped. But there are additional restrictions in division, and there are additional restrictions in compositions. So there's everything for the composition of functions. So this is going to be a 2-part video, so you'll see 2 different links for this section. And then I'm going to make the video for inverses, which is the last section in chapter 3. So be on the lookout for that today, and I'll see you guys soon.